So in this video, we're going to be looking at how you can use TurbSim, which is one of the modules or tools developed by OpenFAST and Nreal in order to generate some turbulence wind data for a wind turbine system, not a wind farm, but just a singular wind turbine system. So within this video, we are looking at the dilemma of predicting wind data, why it's actually important, and to see why it's necessary to go through the different methods and approaches in order to generate turbulent wind data. Then we're going to look at the established turbulent models. Then we'll go on to criteria for selecting which model is relevant or which model is applicable for the current problem or circumstance. From there, we'll move on to TurbSim. We're going to use the TurbSim application or module in order to generate a .bts file, which is the wind data that is used by inflow wind. Then we'll go on to Nreal tools for data generation. For example, you can generate hydrodynamic data, which is data from waves at the sea. So assuming you have an installation in those kind of environments, you can generate the data using these modules. And with these tools, you can then convert it and use them in other applications aside OpenFAST. Then we'll go on to look at OpenFAST community, where you can actually go register, ask questions, and find the solutions to your own problem. So looking at the dilemma of predicting wind motion, wind can be random in most cases. So you may say it's stochastic, and there are different methods used to measure the wind speed. So there are times where you can actually use a sonar, a lidar, or a wind vane to establish what the wind speed is in a particular location. Let's say you want to install a wind turbine there. You put some of these instruments and you measure the wind. Probably you get your mean, your standard deviation, and other information for this just one location. But wind in itself, wind varies in terms of the horizontal plane. Let's say the wind is moving from 0 to 5 kilometers away on the ground, horizontal plane. The wind can vary from one value to another. Aside that, wind can also vary due to temperature and other environmental conditions. Also, wind varies in the vertical plane from the ground where you are going up within the atmospheric boundary layer. There's a certain pattern that the wind follows. So the atmospheric boundary layer is within about 1 kilometer or more. And after that, you enter into a different layer where probably the wind propagation with the vertical is inverted, so it changes. But within the atmospheric boundary layer, the wind changes according to probably the log law or the power law. But these things vary. But when you have a large scale implementation, you want to implement for a location that you cannot actually install your instrument, then you need to find other methods in order to generate your wind data. So you can see here the wind is actually on the left, which is the red, and the U is like sort of like your mean velocity coming to the wind turbine. So there are some models that can provide you data, wind data, for a two-dimensional plane. So for X and Y, just before or on getting to the wind turbine. So what happens to the wind turbine afterwards is of no business of this kind of models, which is what they do. There are other models that can actually show you, oh, for a certain distance, as the wind is coming in, it's changing until it gets to the wind turbine. So you're talking of three-dimensional data, but it's only just before it hits the wind turbine. And that information is no longer relevant after that wind turbine. But let's say a case where you want to install a wind farm. And this wind farm, you need wind data beyond just the first wind data getting to the first wind turbine. What are the data behind the other wind turbines? You then see that you need more information. So it's possible to say, oh, after this first wind turbine, we are going to put instruments behind this wind turbine to see how the wind propagates before it gets to another wind turbine, or by distance, how is it going to be estimated. These things cost money, so we'll discuss it later. These things cost money in order to generate it. But if you are doing different projects at the inception or initiation phase, you don't have so much money to invest into doing actual analysis of wind data or how it's going to vary with respect to the environment you are going to, which is one of the reasons why you need a model. You need a computer program that is able to model this wind propagation just before the first wind turbine and beyond subsequent wind turbines. So you need three-dimensional data And and you're not talking about 4D or more than 4D of information, because you need X, Y, Z. You also need in time space. So as it varies with time, the wind speed is going to be changing along the line from one location, the initial boundary condition to the final boundary condition, as well as all the forms or landforms within those initial and final boundary conditions. That's where you need more complex models of turbulence wind simulation. So when you're talking of turbulence models, it's basically divided into three. So you have stochastic, you have CFD, and you have engineering wake models. So stochastic has to do with, is similar to when you have statistical methods being used or pseudo-statistical methods. So it's partially statistic. So you can use the mean wind speed, you can use the standard deviation. Then other parameters are used to model this wind. In most cases, these kind of parameters are in two-dimensional space. You do not have it in time space. So it does not vary according to time or in distance. It's just at a plane. It's just a plain two-dimensional wind data that you can generate. If you then need three-dimensional data that changes, or four-dimensional data that changes with time as well, that's when you need computational fluid dynamics. Everything that has to do with computational fluid dynamics involves the Navier-Stokes equation. So it involves solving of Navier-Stokes equation, which is what is being done in CFD. So under CFD, you have the direct numerical solution. After that, you have the Reynolds averaged Navier-Stokes. Then you have the large eddies simulation. After this, you then have the DES, which is a combination of a solution of the shortcomings or the cons of RANS and the cons of LES. Meaning that because one of these is computationally expensive, for example, LES is computationally expensive, DES actually solves it. And because RANS is not as accurate as LES, this DES solves the problem of RANS. So the cons for both of these approaches are solved using DES. And from there, you are then able to have a more workable solution. So the detached eddy simulation is a combination of the approach to LES and RANS. So the detached eddy simulation solves the shortcomings of those two other methods. So CFD has to do with solving the Navier-Stokes equation, which provides four-dimensional or more data. It provides you your wind speed in all directions as well as in time space. The benefit of LES, as is used for OpenFAST, is that once it comes into contact with an object, for example a wind turbine blade, the pattern of movement, the deviation after it hits an object is well modeled, which is one of the reasons why LES is mostly used for OpenFAST. Then with respect to engineering wake, similar to what I said earlier, when you have your measuring devices in front of a wind turbine, you measure the wind speed and other statistical data. And after a wind turbine, you then place other instruments and then you measure the wind behind this wind turbine at different distances behind the wind turbine. You will see how the wake, which is the wind speed or wind profile behind that wind turbine, it's recovering. So once it goes through the wind turbine the first time, it loses some energy. So the wind speed drops, but over some distances, it recovers. So all of this is captured with different devices. So in those experiments, you can then vary the size of the wind turbine. And at some point, you are able to see a pattern, which is how these engineering wake models have been developed by Jensen, Franzen, and the Gaussian approach. So from left to right, Jensen doesn't consider turbulence that much. That's the effect of turbulence. However, Franzen considers it more, and Gaussian considers it more than both of the two initially. So turbulence consideration increases from left to right. I also say that this engineering wake model is less computationally expensive as the CFD models. So it's quicker to generate the data from this approach. So we are going to select a model. Let's say you want to work on a wind turbine system or a wind farm. Which approach are you going to choose? So you need to consider, there are 5 different judgments you need to make in selecting what kind of model will be preferable for that case. So each of them are getting 20%, but it doesn't necessarily mean the level of decision on each criteria is equal. It may actually vary. However, we have just separated it into 5 equal places. So the level of description is important. So for the DNS, you're going to get 3-dimensional data in a time series. So it's like 4D. You're going to have information varying with respect to the time plane. With respect to mixing length model, it follows similar to, it's just 2 directions you're going to be getting your data, not in all directions as much as the DNS is going to give to you. So if you have a wind farm that you need 3-dimensional data, you'll be going for the DNS or every other CFD model, not something that is not going to completely express the information that you need from the analysis. Criteria is completeness. There are some equations, which are the models, that only require your initial boundary and your final boundary. Everything else within the environment of those boundaries can be estimated based on the model. That's a perfect example of a complete simulation or a complete model. But there are some cases where when you specify initial and final boundary conditions, as this wave of the wind propagates, you then need to specify other information, or you need to isolate different kind of flow patterns in order for that model to work, meaning that that model is not complete in itself. You have to specify other criteria within the simulation. So cost and ease of use. There are different ways to estimate the cost of a particular model. For example, statistical probability functions could be easier to estimate. But when you are talking of Navier-Stokes and you are talking of the time plane, 3-dimensional data plus time, they are talking of several equations that need to be solved. So it's a very large matrix that you are developing. And probably, let's say you are running into 5 kilometers, and then the distance that one is taking is about 50 meters. So there's a lot of equations that are being solved along the line. When a computer program is solving this equation, it takes time. And this time is an expense. And once the program has been completely run, when it's storing, the megabyte storage too can also be an issue. So all of these have to be considered, whether it's a trade-off you are willing to accept in selecting that kind of approach for your modeling of your wind turbine system or wind farm. So range of applicability, like I spoke earlier, there are some points. Like I spoke earlier, there are some models that just give you 2-dimensional flow, others give you 3-dimensional flow, and in the time space. So if it does not have the required properties for your model or your requirements, you cannot apply that model for the problem at hand. Lastly, the level of accuracy. So accuracy is a measure of how well the model performs when it's compared to real-world data. So assuming you use certain parameters, you run your model, the output result, you then compare it with what was done with instruments on the field. You can then determine the accuracy. So there are already established accuracies from each of these models. It's available in literature, so you can actually select based on recommendation from those literature. So now we are on TurbSim. We are going to generate data for TurbSim, which is the .bts file, for it to be used in OpenFAST. So you see here the user guide for TurbSim. It's available on the website. So this is TurbSim user guide, which is used to generate 2-dimensional data, turbulence data for a wind turbine. You have several instructions before it talks about the input file and how to edit the input file. So this is version 1.5, but there's also 2.0, which is from 2016, but it says drafts. However, you can still make use of it. Most of all these are for testing and analysis. It's not a commercial software, so you have to make do with what is made available. So you can see if you come to nrel.gov/wind data tools, you'll be able to see the different. You can see here the different modules and tools from which you can then use to generate data for other purposes. So you can see TurbSim here. So if you go to TurbSim, you can then see different instructions on what it's all about, as well as the user guide. It can be downloaded from here. So if you have run the application from part 1 of OpenFAST, you can see how to generate, to copy all the files. So these are some of the files that were copied from OpenFAST on GitHub. So you can see here, this is TurbSim, and we are going to use this TurbSim for this analysis. So once you've navigated to, you found a way to get to your 5 megawatt baseline folder, you can go to part 1 of this video series. You will find it there. So in the 5 megawatt baseline folder, you will see several files. There are several files in the 5 megawatt baseline folder, and here you see inflow wind 12 meters per second. All of this inflow wind, as long as there's no steady here, they are all turbulent flow. So you see steady 13 meters per second, steady 8 meters per second. Those are all steady flow, but the ones that don't have steady on them, they are actually turbulent flows. So if we were to, let's look at this 12 meters per second, which was built into OpenFAST, what was downloaded online. So let's say we go to the 5 megawatt baseline. This is Visual Studio Code. This is the same folder we're looking at just now. Under 5 megawatt baseline, you can see here inflow wind 12 meters per second .dat. So you can see several information here. You can see the height of the hub, the exponential used for the power law, then other information. You can see that .bts was generated. So this inflow wind 12 meters per second is referencing this .bts file. So most of the data is coming from this .bts file. This .bts file can be found in this wind folder. You can see here .bts, so 12 meters per second .bts. Because I've generated some wind information before, I have it here. So this is it, 12 meters per second .bts. If I want to generate their own turbulent wind data, so with this, if we're going to generate data for a turbulent wind data for, let's say, 15 meters per second. So we come to this folder under the 5 megawatt baseline, and in order to maintain the original files that were generated from OpenFAST in GitHub, we just copy what is here and we change it, because we want to generate a 15 meters per second mean wind speed for turbulence. So that's the input file that is being edited. So under this wind folder in Visual Studio, we'll select that file, then we'll change what we need to change. So let's say we want to change it from Keimal to von Karman. We can do that change. Then anything else, if we want to change it to log law, we can put log there. If we don't want power law, we can put in the log law and any other information we want to change as required. So all of this will make the changes, then you can save the file. Once the file is saved, then we come back to this folder here. So we are going to generate the .bts file. So as we are working, you can look at this folder where we have the wind files. So we select the 15 megawatts we just generated and drag it over TurbSim executable file. You will see how the files under wind are increasing. So you now have a .bts file and a .sum file for the 15 meters per second turbulence model. So that's how you do it. Wait for all the components to be generated. So once these files have been generated, it's then possible to proceed, because all the details have been packed within .bts file. So we come to inflowind.dat file. We can pick any of them, but since this has already been generated before, it came with OpenFAST, the 12 meters per second. So we just copy it and we paste. The name will change to, I'll change the name to 15 meters per second and remove everything else. So in the text editor or programming, I'm going to edit. You can see here the inflow wind 15 meters per second of that. The wind type is binary TurbSim flow field, which is wind type 3. So 1, 2 will not be run. It's this item 3 that will be run. Here will be run. And because I've generated a .bts which is 15 MPS, so I change that to 15. If other file name is used, we can then copy and place it inside here. But for simplicity, I've used that here. So those are the information. If there's anything else that needs to be adjusted, it can be done here. But in most cases, you hardly need to do much of that. So once that is done, looking at the aerodyne, it doesn't take any input from inflow wind. So you're not editing any of the values in this .bts file. So assuming we want to run this file, ITI badge, 5 megawatt ITI badge.dll wind turbine. So if we come to the .fst file, you can see that when it's talking about the input files that will be used to run the program. You can see here the wind file, the inflow wind. And because we have changed our own values, we'll not be using 12 meters per second, we are going to be using 15 meters per second. So we change it to whatever the file name is, but in this case, I've just changed the 2 to 5, which because I'm using 15 meters per second. So whatever the case, this folder, the location of this file has to correspond with what OpenFAST has done in generating this program. So if this file is placed in a different folder, either you are changing the whole of this file name or you are relocating this file to that folder that OpenFAST runtime is pointing to in order to avoid any errors. So that's basically it. So you can edit other information and it will run accordingly because all you need is the input file that you generate, the .bts, run it. You identify the location of where you are running it, and that's it for running TurbSim to generate a .bts. So there are several data tools that can be used to generate information for either OpenFAST or for other programs. For example, you can use Hydrodyne module to generate data for a different program. Probably you want C-state data for a different software. You can use any of these simulators to generate that information that you need. Simulators or preprocessors, they can generate those data, and that data can be captured and taken to another application. So here you can also see user manuals and other information. So it's nrel.gov/data tools. All that is required will be obtained from this part of the website. So there's also a forum online where one can create, if you are doing the research, you can actually create a page. So you have to contact the managers of this page on NREL in order to create an account. Then you can ask questions. If you go to this forum, you can ask questions. You can also browse the information about issues that people have faced before, how they handled it, in order to understand better how to run and make use of OpenFAST. So you can see it here. This is forums.nrel.gov. You can see here different topics have been discussed at different times. You can also try and create an account if they will approve, but you can try it. Apart from that, you also have from OpenFAST on GitHub. They also have a forum there where you can ask questions, read comments. That first of all, you need to read a lot of the comments here to find out about the problems people experienced and how they were able to solve it. If you don't see a question that interests you or a response to your own challenges, then you can then ask your own question when you've confirmed that it's a new question that hasn't been treated before. So these are ways that we can actually improve ourselves using this program for research purposes. So thank you for watching this video. This is Catchment of Resources. Remember to like this video as well as subscribe to the channel. This is Catchment of Resources, where we create for better living.